let's say I'm over here. I'm going to do two scenarios. So I'm an observer over here. This is me. This is me. And then maybe even better, I should just draw my eyeball, because we're going to be observing light. So I'm just going to draw my eyeball. So this is me in the first scenario, and then this is one of my eyeballs. And then this is one of my eyeballs in the second scenario. Now in the first scenario, so let me draw it. So in both scenarios, we're going to have an object. We're going to have some type of source of light. But in the first scenario, relative to me, the source of light will not be moving. While in the second scenario, the source of light, just for the sake of discussion, just for fun, will be moving at half the speed of light. Unimaginably fast speed, but let's just assuming it is. So it's moving at, it has a velocity of 1/2 the speed of light, 1/2 light speed away from me. Light speed away from me, who is the observer. Now let's just imagine what would happen. They're both emitting light. And they're both going to start emitting light at the exact same time. And when they start emitting light, they're both at the exact same distance from my eye. The only difference is that this is stationary relative to me, while this is moving away from me at half the speed of light. So let's say that after some period of time, that the light wave from this source reaches my eye. So, and then it looks something like this. I'll try my best to draw it. So let's say I want to draw a couple of wavelengths here. So let's say that's half a wavelength. That's a full wavelength. That's another half, a full wavelength, another half, full wavelength, and then a half, and then a full wavelength. So let me see if I can draw that. So it would look like full wavelength, full wavelength, full wavelength. This is not easy to do. And then you get another full wavelength. So it would look something like that with the actual waveform. And so that this is just the front of the waveform is just getting to my eye. And then as the waveforms keep going past my eye, my eye will perceive some type of a wavelength or frequency and perceive it to be some type of color, assuming that we're in the visible part of the electromagnetic spectrum. Now let's think about what's going to happen with this source. So the first thing is that the front of the waveform is going to reach me at the exact same time. One of those neat and amazing things about light traveling in general, or especially in a vacuum, it doesn't matter that this is moving away from me at half the speed of light. The light will still move towards me at the speed of light. It's absolute. It doesn't matter if this is going away at 0.9 the speed of light. The light will still travel to me at the speed of light. And it's very unintuitive, because in our everyday sense, if I'm moving away from you at half the speed of a bullet and I shoot a bullet, the bullet will only move towards you at it'll kind of that half of its velocity will be subtracted, and it'll only move towards me at half of its normal velocity relative to whether it was stationary. But not the case with light. So with that out of the way, let's think about what the waveform would look like. So by the time the light reached here, we need to think. Let me actually redraw this over here. Let me redraw this eyeball. Let me redraw this eyeball right over here. So this is me again. So by the time the light reaches my eye, so they both started emitting the light at the exact same time. This guy has traveled half this distance, right? If it took light a certain amount of time to get this far, this guy will get half as far in that same amount of time. So by the time the light reaches my eye, this guy will have traveled about half that distance. So he would have traveled about that far. But they started emitting the light at the same time. So that very first photon, if you view light as a particle, will reach my eye at the very same time as the very first photon from this guy. So the waveform is going to essentially be stretched. So instead of having, so we're still going to have, see, we're going to have 1, 2, 3, 4 full wavelengths, but they'll now be stretched. So let me see if I can draw 4 full wavelengths. So let me cut this in half over here. Let me cut each of those in half. So each of these are going to be a full wavelength, and then they're going to have a half wavelength in between. And so the waveform is going to look like this. Let me try my best to draw it. This is the hardest part, drawing this stretched out waveform. And there you go. It's going to look like this. And so when it gets to my eye is going to perceive it as having a longer wavelength. Even though from the perspective of each of these objects, if you're traveling with each of them, the frequency and the wavelength of the light emitted is the same. The only difference is this guy's moving away from me, or I'm moving away from it, depending on how you want to view it, while I am stationary, or it is while in this first case, the observer and the source are both stationary. Now, in this situation, what's my eye going to say? Well, my eye will get each of these successive pulses, or each of these successive wave trains, and it's going to say, hey, there's a longer wavelength here. There is a longer wavelength, a perceived longer wavelength. Let me write that. A perceived longer wavelength here, and also a perceived lower frequency. A perceived lower frequency. So what would that do to the perception of the light? Let's say that this is green light. So if we were stationary with the observer, it would be green light. So let's look at the electromagnetic spectrum. I got this off of Wikipedia. So if I was stationary with the observer, we'd be in the green light part of the spectrum. So at a 500 nanometer wavelength. But if all of a sudden, because the object is moving away from me at this huge velocity, the perceived wavelength becomes wider. So from my perception, it's going to have a wider wavelength. And you can see what's happening. It will look redder. It will move towards the red part of the spectrum. And this phenomenon is called redshift. This is called redshift. This is redshift. And I've done a bunch of videos in the physics playlist on the Doppler effect. And over there, I talk about sound waves and the perceived frequency of sound as something travels towards you versus away from you. And it's the exact same idea. This is the Doppler effect applied to light. And the reason why the Doppler effect works for light traveling through space and for sound traveling through air is because a sound wave in air, regardless of whether it's moving away, whether the source is moving away or towards you, the sound wave is going to move at the speed of sound in air at a certain pressure and all of that. And light is the same thing, but in a vacuum, it will always move, regardless of the source, regardless of what the source is doing, the actual light wave itself will always travel at the same velocity. The only difference is that its perceived frequency and wavelength will change. And now the whole reason why I'm talking about this is you can use this property of light, that it gets redshift, to see whether things are traveling away or towards you. And people talk about redshift because frankly most things are traveling away from us, and that's one of the reasons why we tend to believe in the Big Bang. The opposite, if something is traveling towards me at super high velocities, then we would have something called, and you don't hear the word, it would be violet shift. The frequency would increase. The frequency would increase, so it would look bluer or more purple. Now the other thing I want to highlight is this redshift phenomena, this idea. It doesn't apply only to visible light. So it could even apply to things that we can't even see. So it would become redder, but it's not like you can even see. It could even be applied to things that are even more red than red. So maybe it's a microwave that is being emitted, but because the source is moving away from us so fast, it could be perceived as an actual radio wave. And actually, I should have talked about this in the video on the microwave background radiation, is that we're perceiving it as microwaves. But the sources were moving away from us. They were being redshift, so they were not actually emitting microwave radiation. Just what we observe, and this is actually what would be predicted based on the Big Bang, is actually microwave radiation. So anyway, hopefully that gives you a sense of what redshift is, and now we can use this tool to explain why we think many things are moving away from us. And now let me just actually make sure you get that idea. If I have two objects, let's say that these are suns. Let's say that these are both suns, or both galaxies, either way. And because of other properties, and I won't talk about them right now, we know that they are probably emitting light of the same color. they're probably emitting light of the same color because we know other properties of that star or of that galaxy. Now, if what we actually perceive is that this one looks redder to us than this one, then we know that it is traveling away from us. And the redder it looks, the more its wavelength is spread out relative to this other star, the faster we know that this is moving away from us.